In this video, we're going to focus on learning about function notation and then getting into linear functions with a little bit of modeling with linear functions. So we're going to determine, again, if a relationship is a function and in fact is a linear function, and determine its domain and range, along with graphing the function and building linear models. But most importantly, we're going to be focusing on function notation. So before we were talking more about relationships as ordered pairs, function notation is usually how you're going to interact with functions in terms of equations. So equations and symbolic representations of functions typically will use function notation. So thinking about a function as an ordered pair, what this is really saying in terms of function notation is, say if we have a coordinate x comma y, all right? This represents an ordered pair given by a relation. We know it's a function, all right? Later on, I'll give you an example with a table. But what this is really saying is that we have this new notation, say f. F assigns something in the domain to something in the range. And in this case here, f assigns the value x to the value y. So as an ordered pair, this is really x comma f of x. So this really reinforces the idea is that this is the input, and then f of x is now your output. So commonly you'll see this f of x is equal to y. That means that this is a function in function notation. And it's assigning the input x to the output y. So f is a function taking x to y. So again, the parentheses here indicates you're inputting something. So in this case here, for instance, f parentheses, this is to indicate you have an in and then you have an out. I want to reiterate that. F with those parentheses around it means in and out. And one other notation, this is something good to know, is that sometimes you'll see F with square brackets differentiated from parentheses, which can also often be misconstrued using distribution or a multiplication coming from ideas from algebra, where you see like x parentheses y typically will mean x times y. Here, this does not mean multiplication. So this is not multiplication. I want to point out is that we'll be using this parenthesis one because that is the notation that our textbook uses. In some other contexts, some people do use square brackets, but the common notation is using parentheses. I just find that talking about the square brackets here kind of helps you with like, oh, this is a little bit different than parentheses is really defining an in and out. A very common problem is to find the values from the table of a function. So for instance, this is a table designating a function. You can tell it's a function because you have for each input one output. Now it is completely okay that outputs are repeated, but you only need to have one output per input. So for instance, to know it's not a function in a table is that if you see a repeated x value with a different output value associated to it. So in this case here with this function notation, this f of x here is replacing y. So this is y is equal to f of x. So for instance, an ordered pair, in this case here is the notation x, f of x, replacing y there. And for instance, the first point here, this one, corresponds to the ordered pair -1, 0. So what this is telling you, then if I give you the value, okay, what is f of -1? Well, thinking about this as an ordered pair, this is the point -1 comma 0, reading this off from the table here. And so f of -1 is equal to 0. So this is using function notation, reading it off from a table. Likewise, f of 0, taking a look at our table here, f of 0 is associated to this. So you first find that 0 in your table as your input, and then you read off your output. This is equal to 3. Likewise, f of 1, that means that we go to the input of 1, so we find our 1 on the input, and then you come down to your output. That is also 1. And then lastly, taking a look at this, we have a 2. We input 2, we have an output of 1. So that means f of 2 is equal to 1. Next, another common question to have is find the inputs associated to an output. So say we have f of x is equal to 1. What x values work? So what this is saying is that our output is 1. All right? So that means our output is 1. So then we go to our 1s on the outputs and we find our inputs. So the possible inputs can be both this one here, so the 1, and then a 2. So this is asking for what inputs give us a certain output. So this is sort of asking a sort of an inverse question, which we'll talk about a lot later. This is asking what inputs give a certain output. So thinking back to the assigning text to people situation, for instance, if you want to know who is giving the presentation, that is asking who did you assign that presentation, do the presentation to? And so do the presentation, we assigned it to Carol. Carol is doing the presentation. So I'm asking who is doing the outcome of the presentation, and the answer is Carol. Likewise, who is doing the data analysis? That is asking, okay, the output we want is data analysis. I need to talk to the person needing to do data analysis. Then we go back and ask the person doing the data analysis, which is Alice, the question. To wrap this section up, we're going to talk about finding the values of the function f of x is equal to 2x minus 1. So this is a symbolic representation of the function. So using function notation is that we're representing this function f of x with the values of 2x minus 1. The first thing you should notice is that this is a linear function. Because if we consider the line y is equal to 2x minus 1, points on the line are of the form x comma 2x minus 1. If we assign here our y value, well, what do we already do there? Well, this is just x comma f of x. So what this is telling you is that the function f of x is equal to 2x minus 1 represents a linear function. When you input an x value, it outputs a y value on the line y is equal to 2x minus 1. So that gives you sort of an intuition with what we're doing here. So if we want to find the value of, say, f of 0, well, first off, what is this? We're plugging in x is 0. So this is your input is x is equal to 0. And this is, in fact, going to be your y-intercept. That's a good connection to have. So when we evaluate our functions in terms of a symbolic, what that means is that you replace x with the input. That's why I wrote x is equal to 0 here. So in this case here, this is equal to 2 times 0 minus 1. Again, notice is that there's parentheses here. Do that in another color. Parentheses here, and I'm replacing x with the same thing inputted with parentheses. So every x, you replace it with the input 0. And now it comes down to an algebraic equation that we're going to be reducing. So this is 2 times 0 minus 1, which simplifies to negative 1. So what this is saying is that then f of 0 is equal to minus 1. So this is in fact, our y-intercept. So this corresponds to the point 0, comma, minus 1 on the graph of that line. So this is a good connection to make, and why linear functions are quite nice. It's another way of writing functions. In fact, any non-vertical line can be written in terms of function notation. The issue with vertical lines is that they're not a function. They fail the vertical line test. Any other type of function can be represented using function, or linear function can be represented using function notation. So like if you have a line with some given slope, it can be 0, or any number, then you can represent it as a linear function. If we want to evaluate at some other value of, say, 1/2. So again, what this means is that our input means x is equal to 1/2. That is essentially looking at the x-axis going to 1/2 and figuring what that y value is on the function. And then to do that is that you plug it in. So now we have 2 times 1/2. You notice I'm using a parentheses here, and that notation should carry over. So for instance, we have a parenthesis here and a parenthesis here. And then finishing up the equation, we get a minus 1. And now we simplify this down. So we have 2 times 1/2, which is 1, minus 1, and that is equal to 0. So then, assigning the point 1/2, we get the value 0. So f of 1/2 is equal to 0. In fact, this is our x-intercept. And you can see that by f of 1/2 is equal to 0. Or if you set y is equal to 0 in the equation, you can solve for x and see that that is in fact x is 1/2. So this is our x-intercept. But this is how you evaluate functions at a given value. So if I give you a value, f of x is equal to a symbolic representation, when you plug in a value, you replace all of the variable x. X here represents the input. You replace all of the inputs with the number you plugged in.